Hello from Augsburg. Nice to have you here. Welcome at KUKA. Today we're going to have the chance to have a look behind the scenes, and we will look into our application engineering. And of course, this can only be about robots. Robots are quite fascinating machines, but the same goes for the production processes where our robots are working 24/7 around the world. That's the reason why we also look on these processes, and we always try to optimize and think how we can improve or make processes more efficient based on robot automation. When you approach a task like this, there are two possibilities. First possibility is you have in mind how a robot works, you look at the production process, and you try to match the process to the capabilities of the robot. So the process needs to be changed. The other way around is you try to keep the process as it is and try to empower the robot with a special gripper technique, with external access, with software technology to make it able to keep the current production process. Based on experience, we can say if you want to have a really good solution, you need to do both. That's quite for sure. But that is exactly the point where it starts to pay, because the KUKA mission for 2030 states automation is going to be more easy, it's going to be simpler, we will reach much more people, and based on this, we will also enter a lot of areas where we don't see automation today, but we will see it in 2030. So for today, of course, we prepared an example. We will see a fenceless application with our assembly in motion. Much more important than the application itself is that we would like to inspire. We would like to give you some ideas and also some solutions, what needs to be considered, what needs to be done when you have applications like this within your production lines. I'm happy that two of my colleagues, two very experienced colleagues, will support me with this today. My name is Christoph Hock, and within KUKA, me and my team, we realize applications within the field of human-robot collaboration, and especially we focus on the final assembly area within the automotive industry. Let's go. Okay, here we are, almost standing within the application, and for me, that's the perfect moment to hand over to my colleague Ottmar.
Yeah, hello and a warm welcome here in the assembly in motion setup. My name is Ottmar Honsberg and I'm responsible for the application engineering here at KUKA. I think you know a lot of robot applications where we have different processes like welding, screwing, handling or assembly. So most of them have the same situation, that the robot is fixed, the parts are fixed, and then the robot is moving position controlled on a nearly blind way to the part and doing his process, as I mentioned before. When we do the engineering of a new application, we have three key points which we have in focus. One is the process itself, so the adding value on this application. Then we have the position, how does the robot find its correct point on the part. And the third is the safety. Safety for the worker, but even the safety for the part itself and for the equipment.
The best example for what Ottmar just described has been realized, and I'm thinking about the body in white. Within body in white, the degree of automation is incredibly high. We're talking about something in between 80 to 90%. But there are also areas within the automotive production, like the final assembly, where the degree of automation ranges anywhere in between 10 to maybe 20%. Of course, that has a reason. You cannot simply compare those two areas. There are very different requirements. And just to name two a bit more detailed, I'm thinking about the work steps itself. So when you picture how a worker assembles wires, assembles a spotlight, that is something that needs to be done with a high sensitivity. So the human is perfectly suiting this task. And then a second thing that comes with the final assembly is the flow operation. Flow operation is an organizational tool that you need to use when you are faced by a high number of variants. So there are so many different parts on the same conveyor that needs to be worked on. And the flow operation brings lots of flexibility into that. So simply from what's given and what you receive, we have the best output ratio.
Yeah, this makes sense. Now we have to think about the question, how can we combine this full automation in the body shop, for example, and the flow operation, as you explained. What is necessary and what do we have to think about when we want to bring more robots in the flow operation area without disturbing the environment by putting in a lot of fences? So for that use case, we have prepared an application gap and flush measurement. So we did this previous here on this setup. Yeah, what is gap and flush? When you look on your new car, then you see the two doors, for example, and there is a gap between these parts, yeah? And you want to have it parallel, it looks nice. And there is necessary that the flush, so it's the deviation on that area, how is this adjusted? Because if it's wrong adjusted, then you get a lot of noise during you driving the car. So this gap and flush quality measurement can be done by manual measurement devices, like a caliper, or with automatic tools like an Enos dual head we have used here in this application. For this, it's necessary that if the part is moving, the robot has to follow very synchronized, that during the measurement you have no velocity deviations. Yeah. If this happens, correct, then you can analyze these values and do some statistical analysis or make some correction in the assembly. Yeah, so this is the process. To do this on the part, in motion, there we need some additional technologies. So we have the trigger. So the trigger gives the signal to all surrounding systems. Now we start. Then we have the pre-measurement system. This system is looking where is the part at a certain time. And the third is the encoder, which gives us continuously the movement of the conveyor. The trigger starts, all systems are running, sending the robot a frame for correction of the relative position, and then the robot starts moving on the pre-programmed position and is synchronizing on the points where the measurement should be done.
Okay, okay. So we've talked about the process, we've talked about the position where we get it from, but we are faced by flow operation again. So in this case, what are we going to do about the safety?
Yeah, safety, very, very important question. The safety in the assembly motion is a very tricky thing, and we thought about it, and we find some special things on that. So what's happening? If we have a cobot like an LB or EVA, and it gets a collision detection, the robot closes the brakes, and then the robot is stiff. You have the part, in this case the car, is moving constantly, and if the worker is between the car and the robot, which has closed the brakes, then you get a clamp situation, which is definitely forbidden. Yeah. So we have to solve this situation for the worker. And therefore, we have a retraction unit. So if we have a collision detection, then we move out the robot in safe conditions. So, and here is this retraction unit we built specially for this kind of applications, and we can have a look on that now.
Okay. So what needs to be done to get it into the process, on the process?
Okay, actually we have the situation that it's released. So when we bring it to working position, I rotate it to 0 and move it forward. Then I load some springs inside. Now it's ready for operation. Yeah. If now the trigger would start the systems, the robot starts moving.
So if I'm the worker now and I'm just jumping in and I crash with the robot?
If you go in,
okay.
So what's happening? Okay, the robot is moving back without any additional energy, and you can rotate the system. So if you are between the car and the robot, you can release this situation, and you have no clamping anymore, and it's a safe application on that.
Okay. I mean, but this is quite a small robot, a cobot, and I think lots of our customers, they also are dealing with applications where a higher payload, a wider range might be required. And about this topic, my colleague Michael can tell you something.
Thank you, Christoph, and welcome also from my side. My name is Michael Heinrichs, and I'm application developer in the field of global application engineering, and I've been working with collaborative robots since more than 8 years now. When you want to use a standard industrial robot on a conveyor belt without any additional safety fence, it is necessary to use some additional safety features. One technology you can use here is, for example, the airskin technology from the company Blue Danube Robotics. This is a pressure-sensitive skin that triggers a stop when you have a collision with the robot. The manufacturer already offers ready-to-use retrofit packages, for example, for this KR CyberTech. So one benefit is that you can nearly retrofit it to all standard industrial robots, and that you can use classical industrial robot programming. That means you can reuse interfaces and also your already available programs. But now I would like to hand over to Christoph again so that we can see the application running.
Okay, here we go. So the application is already running. The conveyor belt's velocity is more or less exactly the same that we know from a typical final assembly area. The robot has the KUKA conveyor tech on an KSS 8.6 installed. And what the robot now performs is a very simple scan of all visible labels. It's doing it on our new KRC5, and we just do this as an example to validate, to document that the assembly was done well in the correct way. Another example would be that we could check all the plugs, whether they are attached correctly or not, also as a quality indicator. On the KR8, also the label will be scanned, and depending on what camera you put on the robot, it could be also possible to check the paint's quality. I'd like to emphasize what we can see here is that it is even possible to do a complex pass process. So the robot did not even follow a point, but a very circular way around the robot's base. Okay, so we have talked about the process. We know where we get the position from, and now it's time to talk about safety. We're going to simulate a crash. And what we saw, what happened, is a combination of different safety features. So the robot stopped, the belt stopped, the effector is also patched into an airskin, and it also dropped. And given that, we have a very good set how to make these kind of applications more safe.
Christoph, you see, fenceless robot application with assembly motion combined is possible. So I think not everything will work, but the door is open.
And that's why we would like to go the next steps with you together within this new field.
Industrial intelligence.